Hey everyone, this is Brian, back again with another video lecture for CSC143. In today's video, we're going to be learning more about recursion and how the stack makes it possible, as well as a slightly different strategy for writing recursive formulas known as tail recursion. First, let's start out with a recap of what recursion was. We learned about this new data structure, the tree, which was kind of an extension of the linked list, where we had several nodes composed in the structure that each can have children nodes of their own. Trees have a head node, called the root node, much like how linked lists have a head node, which is the very start of the list. Each node can have child nodes. For binary trees, that means each node can have up to 2 children. A node that does not have children is called a leaf node. We learned about recursion as a way to solve problems that were large by cutting them up into smaller and smaller subproblems and composing the composite solution to the entire problem by combining the solution to those smaller subproblems together. Recursion involves 2 big ideas. The base case, which is this simplest subproblem and has a trivial solution, such as determining what the sum of all the elements in the linked list is. We can just examine a linked list that has no elements, or just one element, in which case we just return that value right away. And then the recursive case, where a solution to our overall problem is derived from the combination of our base case and the recursive call to these simpler subproblems. When we break down our linked list problem, for example, we can divide it between whatever is present at the head node that we're currently examining and whatever is present at the remaining side of the list. In the example where I talked about the sum of all the elements in a linked list, we just have to add the value at the head of the list plus the recursive sum of the values remaining in the list. By just examining the values remaining in the list, the subproblem that we're passing to the recursive call is slightly simpler than the initial problem, which is the entire list. And eventually those recursive calls will hit this base case, where the solution is trivial, and start to return a value that will bubble up with these recursive calls, to begin to resolve those recursive calls that we will combine with the base case to form a composite solution to this overall problem. Trees, much like linked lists, are naturally recursive. Every child node of a root node is itself a subtree, that is, a complete tree data structure. One of the recursion examples that we learned was this contains tree method, where we performed a depth-first search to determine whether or not a value was present in the tree. Let's take a look at that code now. Here's my contains tree method. The method signature is as follows. It's a return type of Boolean. It takes 2 arguments, a root node of a tree, a binary tree that is, and a value that we're looking for. Our base case is pretty simple. If the root node is null, that means there is no tree here, there's nothing in the tree. If the root node happens to have the value we're looking for, then we can return true right away. Otherwise, we can break down our problem into subproblems, whether or not the value we're looking for is on the left side of the tree, or whether or not the value we're looking for is on the right side of the tree. If either one of these cases is true, then we can return true. If both cases are false, then we of course return false. The clever thing about this recursive call is because I'm passing in the subtree on the left side and the subtree on the right side, the contains tree call is processing a smaller version of the overall problem. And as the recursion happens, as these calls return back to the top and eventually hit these recursive calls again, we'll eventually hit the base case where I hit a leaf node and there are no more children remaining, and I will have exhausted a particular branch of the given tree. Eventually those contains tree calls will start to return and percolate upwards, up the call stack, and we'll start to combine those subproblem solutions into a composite solution for the overall problem. Now let's actually take a look at this in action in the recursion test.java file, which has an implementation of contains tree. Okay, here it is. I've got the same method signature, I've got the same implementation. Let's go take a look at those test cases and see how it behaves when I start debugging the program. I start out with defining a binary tree node root that has a value of 0, left side of 1 and a right side of 2, and then down the right side branch, I have a left child of 3 and the right child of 4, the same tree that we've been seeing in the other examples. Let me set a breakpoint here at contains tree of value 4. this is going to require contains tree to have to essentially search the entire tree because 4 is the deepest node on the right side of the tree. Let's go ahead and give it a try. Okay, my program is starting to execute. I've hit the breakpoint, so it's now paused. Let's go ahead and click step in and use the arrow keys to pick the contains tree method. Press enter to dive into that method call. And here I start at the very top. My initial call to contains tree is looking for the value of 4, and I have this initial root here as my initial tree location. Of course, I'm going to skip these base cases because the root of the tree does not have the value 4, which leads me to the recursive case. First thing I'll do is look down the left side of the tree, in which I get my first recursive call to contains tree. Let's go ahead and step in. This takes me back to the top of the function call, and we'll see that the root variable has now been updated to point to the left side of the original root. The value I'm still looking for is 4. Once again, not a base case because there is a value here, but it's not the value I'm looking for. So this recursive call is going to try and go one step deeper to the left side. Remember that the left side here has the value 1, and there's no children on the left side of the tree. So when I actually go step in to this point, contains tree is going to go past null to root because the left side of the tree had no children. As you follow along and we start to step into more of these recursive calls, you'll see that the stack frames that are shown in this frames window in the debugger start to increase. In this third level, the deepest that we've gone so far, we've reached the left child of the left branch of the tree, which of course is null. There's nothing here. That's our base case. We can actually go up and down these stack frames to examine the previous calls that we've made during recursion. If I click on the second stack frame, I zoom out to the call in which we had made to this null side of the tree. So here, this was the left side of the root, and then if I go out one more, I get the original root. So the clever thing about the stack frame view is it lets us zoom around and navigate the recursion as it happens. Now that I've hit this base case and I have to finally return a value rather than going deeper, if I step over, what's actually going to happen is it's going to leave this function call because I'm hitting this return statement. And what that does is it eliminates that stack frame that was at level 3 because it had finished the computation necessary to figure out what was there. Now I'm back at level 2, and here where I am is on the left side of the original root. I'll step over and then step into this right side call to go search down the right side of the tree. Sorry, I mean, to be more clear, search down the right side of the left branch of the root. This is going to hit the same base case where I pass in null because there's nothing actually here, and I can return false right away, which exits the stack frame. Now that I've figured out that the value I'm looking for is neither the left nor the right side of the left branch of the tree, I'm actually going to return false for the overall call on the left side, because in left is false and in right is false. The left branch of the tree does not have the value we're looking for, and now I can return back to the initial call to contains tree of root. This completes the assignment for in left, because contains tree of root.left has completely resolved, and we've determined that that's false. Now it's time that we search the right side of the tree. Let's go and step in. We're now hitting a base case. And then we have to once again search recursively the right side of the tree. Remember that a tree looked something like 0, 1, 2, and 3 and 4 down the right side? Here, I'm effectively going to go look down at variable 3. Let's go do that now. I'll go dive in, increases the number of stack frames I have by 1, because I'm at the third layer of the tree. Not a base case, because I haven't found the value I'm looking for. The value I've found happens to be 3. The value I'm looking for is 4. We can validate this in the variables pane if I expand root's payload value. And I see that I have a 3 here. So that's okay. I'll go look at the children of this node that has 3 inside, which of course doesn't have any children. So these two contains tree calls should hit that base case. I'll dive in. I see that root's null. I indeed return false. I step over one more. I dive in, hit the base case again, return false, and exit. Now I've resolved the entire left side of the right branch of the tree. again, to be clear, my tree looks like 0, 1, 2, 3, 4 down the right side. And I've looked at nodes 0, 1, and 2, and 3. Now let's just look at node 4. So let's go ahead and step over, which is going to actually step me out because I'm in a return statement. Then that takes me to the right side. So here now I'm looking at the right side of the right branch of the original tree. Let's go dive in. And I discover that I indeed am going to hit this base case where the value I'm looking for is at the node I'm currently located at. When I step over, because I'm in a return statement, it's going to resolve this call to contains tree, and it's going to eliminate that stack frame. That gives me a composite solution to the right branch of the tree, which has in left of false, but in right true, which is going to percolate up to the initial call to contains tree of root, which then validates that it is the value I'm looking for present on the right side of the tree. And as the composite solution to the entire problem, is the value 4 in the entire tree? Yes, it is. It is because it's on the right side. Okay, so by taking a look at the debugger and how we stepped through the call to contains tree, we got a little bit of a preview of what the stack is. Let's go talk about that now. When I trace the recursive calls of contains tree, we make some observations. The context of each function call is preserved until it returns. Every time we recursively called contains tree, we added another frame to the list of frames. Every time we returned from one of those calls, that frame was eliminated. Each function call can only return when its own recursive calls return. The very first call I made to contains tree for the entire tree, that is just the plain root variable, stayed in the list of stack frames until all of its recursive calls had resolved their own stack frames and their own recursive calls. So what the initial call does is it essentially holds out until all of its child calls have resolved. And this is how recursion is so magical, is because this initial call, which is this very complex problem, waits for all these subproblems to go solve themselves until it itself becomes a sort of subproblem that's going to solve itself and present back to the original caller. These two observations are not just unique about recursion. This pattern of generating new stack frames for each function call and returning and eliminating stack frames with the return statements is the case for all function calls, not just recursive calls. The caller function must save its context, things like local variables, while the callee, the function being called, is running. The callee is going to take up some space for its own context called a stack frame. Then when the callee calls its own functions, and so forth, it must save its own state, recursively, all the way down. Behind the scenes, the stack is responsible for storing the context of each function call, and passing return values from the callees, those functions that are being called, to the callers who are doing the function calling. What is a stack? Recall that a stack is a type of last in, first out queue structure. It's like a stack of heavy plates in real life. Items are pushed onto the top of the stack and popped off the stack in opposite order in which they were pushed. If you have a really large stack of heavy plates, it's very difficult to grab the plate at the very bottom of the stack. You want to grab the plates at the top of the stack instead. This is what the stack structure is going to do for us. When we push on values, it's going to grow the top of the stack. And when we remove values, we're going to do it in the reverse order in which we pushed. The stack test file gives us a quick overview of the available interface. Here I've gone ahead and imported the official Java stack. I'll go ahead and make a stack of integers. I'll push on the values 1, 2, and 3, which ends up with the value 3 being at the top of the stack because that's the last number I pushed on. I see that my stack is size 3 because there's 3 items inside. The peek method examines the top value of the stack, but does not remove it. The pop method is going to return and remove the value at the top of the stack. So the first time I call pop, I get 3. Next time I get 2. Next time I get 1. And after that, after I popped off 1, I have an empty stack. Now that we know how a stack works, let's talk about the stack. The stack is a dedicated space in memory similar to the heap. We've briefly talked about the heap in the past, which is this dedicated space for where objects live. All object instances that are initialized using the new keyword are going to live somewhere in the heap. The stack is another space of memory that's dedicated for preserving function context. The stack stores a number of necessary variables to preserve the context of every single function call. This includes things like local variables, which are of course references in Java, arguments that are passed to the function, which are copied by the caller, and the return address of the function, which is the location of the caller. You'll learn about the return address in more detail when you take a systems course, but this essentially lets the called function know where to resume execution after it returns. Let's take a look at the whiteboard to visualize how this works. Okay, so let's take a look at this right big panel here. I've got the heap, which we've talked about, how it is a location for all objects that are initialized in memory, and then we have another dedicated location in memory called the stack. We can think of this big column here as this is the memory space we can address. Well, I went ahead and put down some memory addresses starting at 0 all the way to 0xFF, which is hexadecimal notation for just let's just call this a large value for now. If I zoom into the stack, let's go examine the contents of the stack, we'll start to see the frames for each function call that I have made. So the very first entry point in Java is of course main, and then if I happen to call something like range sum of 2, that's going to push on an additional stack frame that in itself is going to have stack frames that are children of itself because it's going to go make recursive calls and so forth all the way down. Here's my range sum method. Range sum is going to go add up the numbers from 0 to the integer I that I pass in. It's going to do so recursively as follows. My base case asks if I is 0, if so return 0, otherwise return I plus range sum of I minus 1. So here is a simple main method that's going to call range sum. Range sum of 2 is going to enter the top of this range sum function. In order to call that function, I need to push on a new stack frame. I skip the base case because 2 is not equal to 0, and I return 2 plus the recursive call to range sum of I minus 1, which is range sum of 1. So here we go, 2 plus range sum of 1. This nested function call, the recursive call, requires its own stack frame because once I enter the top of range sum of 1, then I need space for all the local variables inside the body of this function. So here I have range sum of 1. That's going to go compute its own values. 1 is not equal to 0, so it does not hit the base case, and it's going to resolve to 1 plus range sum of 0. Again, with this recursive call, I need to push on a new stack frame, which is going to go onto the stack beyond range sum of 1, and now I hit the top of the function again, range sum of 0, which indeed does hit the base case and returns 0. So here we see that range sum of 0 returns and resolves to 0, which in turn is going to be added to 1, which was the resolution for this range sum of 1 call. That gives me the value of 1 plus 2, which was going to resolve this range sum of 2 call, and finally return all the way up to the initial main statement, which now computes the range sum of 2. Okay, so this diagram is very much like the frames panel that we saw when debugging. Perhaps the only difference visually is that it's flipped. Here I have main at the very top and my stack grows downwards, whereas in IntelliJ we saw how stack frames grew up on top of the stack of frames. There's not really a great reason for this, I suppose. In systems and architecture classes, you're probably going to see this pattern a lot of the stack growing downwards. I think it's a bit more natural because what tends to happen is deeper stack frames have higher memory addresses, and people tend to draw the memory space as being lower memory addresses at the top and higher memory addresses at the bottom. But of course, the behavior is still the same. It still behaves like a stack. We just see the top of the stack as being bottom visually rather than visually at the top here. Okay, now let's formally talk about what's happening. every time a function gets called, including the initial main entry point in Java, the arguments are passed to the function and pushed onto the stack, and space is allocated on the stack for local variables that are made during execution of a given function. This memory region that's consumed by the function is called the stack frame. Now, every time a function returns, the space allocated for the function is popped off the stack because it's no longer needed. Those local variables are no longer necessary because the function is returning. The return value is then copied into the stack frame of the previous function, which is of course the caller of the function that we just returned from. We saw how the IntelliJ debugger is going to show us the state of the stack with each recursive call. As an exercise, I'll leave this to you. Go ahead and try debugging that contains tree method on your own. Let's go ahead and actually visualize it on the whiteboard as a different way of seeing how it behaves. Suppose for a moment, here was my tree. I had the values 10, 4, 8, 6 on the left side and the values 20, 15, 12, and 18, or 24, 21. If I were to naively to look for this value 18 here, and I were to do down, I'll do the same search contains method that I had done in my code. I go down the left side and the right side. I'll start it as 10. I'm going to grab my pen here and circle the values that are relevant. Then I'll go down the left side. I'll see that 4 has no left side, so that's definitely not it. I'll go down the right side, look at 8, not it. Go down the left side of 8, look at 6, not it. Look at 6's children, which are of course not present, so there's nothing here. Then I'll go look at 8's right side, which is not present, so there's nothing here. I'll return false up these recursive calls, and eventually realize that the left side of the tree has nothing interesting. Then I'll go look down the right side of the tree, find 20, find the value I'm looking for, which is 18. I go down the left side, see 15, not the value I'm looking for, so go to the left side of that. I see 12, not there, left, right, not there because there's no children of 12. Then I go down the right side of 15 to hit 18, and I find the value that I'm looking for, which allows me to return true right away. So now I can return true from 18 back up to 15, which is going to return true to 20, which is going to return true to 10, and return true to the initial caller of this function. I do have this remark here. Traditionally, the stack does grow downwards when we draw it in terms of memory addresses, but it still behaves like a last in, first out stack. So again, the whole visualization of us growing the stack downwards as we pushed on frames was just a convention. It is just the visual opposite of what we see in IntelliJ, but practically it's the same thing. It still behaves like a stack. Now let's do some big O performance analysis of trees and algorithms that we apply onto trees. Suppose B is the branching factor of the tree, which is the maximum number of children per node, and D is the depth of the tree. Now let's say we had B to the D nodes in a tree, and let's just call that value n. Now, of course, it's going to cost us O of n memory to actually store the tree. Some quick maths here. Log base b of the number of nodes in the tree, n, is going to get us d. Remember that logarithms are like the inverse of exponents, so taking the logarithm of the number of nodes in the tree gets us the depth, if the base of our log is equal to the branching factor of the tree. Now let's talk about computations on the tree itself. If I need to do an exhaustive recursive tree search, that's going to be O of n in performance because I still have to go look at every single node. It will also cost a certain degree of stack space because each recursive frame that I push onto the stack takes up a bit of memory. If I have a balanced tree, that's going to be up to log of n because the deepest I go into the tree is of depth d, and therefore I'm going to only push up to d stack frames to go make a search happen. However, in the case of an unbalanced tree, that is a tree that has nodes heavily weighted on one side, I may have to actually go to a depth that is equal to n because all the nodes go down one branch. That's obviously not very good because then I'm consuming as much space as I need to actually look down the entire tree. I do want to distinguish these memory costs from the memory costs that we saw when we wrote iterative algorithms. Remember searching a linked list, for example. We would typically do it by just having a head reference, then setting it equal to head.next and walking the entire list. We didn't have to do any recursion. When we use recursive algorithms, we're taking advantage of the stack behavior as a way to allocate space and context for our search. This was not necessary for us when we wrote the iterative algorithms. We only had one stack frame during iteration because we didn't have any recursive calls. The outcome is that iterative algorithms are actually O of 1 in stack space. Recursive algorithms can be O of n in stack space because it requires us to keep track of each function call context and push on additional stack frames per recursive call. So this is one advantage of iteration, which is not recursion. Well, I guess not always all the time, but performing a search without using recursion is only ever going to consume one stack frame because we don't use any recursion. Here there's this certain memory disadvantage of us having to use up additional blocks of memory to store each of these stack frames as we perform recursion. One example of that distinction is path tree search. Remember, one of the algorithms that we first learned when we talked about trees was how we traverse a tree given a path of n elements perhaps. If I have a balanced tree, then I only have to go up to log of n elements deep, which is equal to the depth of the tree, because I only ever have to go from the root to the leaf node if I want to go find something, and I have a path that tells me where to go. It does get to O of n in the performance of an unbalanced tree, where the tree itself is heavily weighted towards one side, and all the nodes line up almost like a list, and my path gets super long and may encompass all the nodes inside the tree. That said, despite this being a tree structure, we can implement the path method iteratively. We don't have to do so recursively. Remember last lecture we learned about how we use the enum left and right to navigate the tree using an array list of enums that took us down the path left or right? We can do that just iteratively. We just have to move the reference forwards left or right given the path that we see. So we don't always have to use recursion when it comes to trees, and when we avoid doing it, we can actually save quite a bit of stack space by having just one frame to use up to figure out the outcome of our algorithm. What about tree insertion? Let's assume that we're only ever trying to insert the leaf nodes at the very bottom of the tree. On average of our balanced tree, then I only have to go to the bottom of the tree, which is depth d equals the log of n. In the worst case, my tree is unbalanced and heavily weighted on one side, and I have to traverse every single node to get to the bottom, which gets me O of n performance. And this is one of those things that, once again, I can do just with one function call. I don't have to do it recursively. I just have to make it to the bottom of the tree. So if I implement this method iteratively, not using recursion, I can get O of 1 memory performance because I only consume one stack frame. Now, compared to the array list and the linked list, trees don't sound that great in terms of performance. To store n values in all three of these structures, we need O of n memory. We can't avoid that, we have n things to store. Array list and linked list both cost O of 1 stack memory to search, because I can just do it iteratively without recursion, compared to log n average stack memory, or O of n worst case stack memory performance for tree search. Here, to search the tree, we have to look through all the values exhaustively, and we have to use recursion. We can't just get away with using iteration as we had did with these linear array list and linked list algorithms. Array list has linear time insertion, which isn't great. Linked list fares quite a bit better with O of 1 insertion, if we happen to do it during iteration, because we just have to wire up the neighboring pointers. Trees, on the other hand, have average log of n insertion cost to reach the bottom of the tree, and O of n worst case, if my nodes are heavily weighted towards one side. So at the outset, you may conclude that, whoa, trees are awful at everything. Why would anyone want to use them? And I think the really magic trick the trees have up their sleeves are a special kind of tree structure called a binary search tree. Binary search trees, or BSTs for short, are a special subset of binary trees, with the following conditions for every node in the tree. All child nodes to the left of the node are less than the current node, and all child nodes to the right of the node are greater than the current node. Let's turn back to the whiteboard for a binary search tree example. Here in my tree diagram on the left, I start out with a root node of the value 10, and the binary search tree rules tell me that all nodes to the left of the root node should be less than the value stored in the root node. So I see here 4 is on the left side of 10, which fulfills that requirement. 8 is also less than 10, and 6 is less than 10. So another way of looking at it is that the entire subtree on the left side of a given parent node is going to be less than the parent node we're examining. The same thing happens on the opposite side, but it has values that are greater than the current node. On the right side of the subtree, we're going to find values that are explicitly larger than the node we're currently examining. So here 20 is greater than 10, 15, 24, 12, 18, and 21 are also all greater than 10. This pattern not just applies to the very root node in the tree, but also applies to the subtrees within the tree recursively. What I mean by that is, if we go back to the left side, and we see that 4 is indeed less than 10, all children to the left of 4 are going to be less than 4, and all children to the right of 4 are going to be greater than 4. So here we see 8 and 6, which are the right subtree of 4, are both indeed greater than 4. But then if I go to the right side and examine node 8, then the same rules apply to this subtree. 8's left side nodes must be less than 8, and 8's right side nodes must be greater than 8. We see the same thing happen on the right branch of the tree. Here, if we look at node 20, all of its left side nodes are less than node 20, and all of its right side nodes are greater than 20. Then if we go one level deeper and start looking at a subtree of this subtree, then we'll see that with node 15, the nodes to the left of 15 are less than 15, and the nodes to the right are greater than 15, and so forth. Binary search trees are going to enable an efficient type of search known as binary search. We've seen binary search in the past when we discussed how to measure big O performance, and we've hinted at how it's so efficient because it cuts the search space in half with every single step. Binary search trees are going to make that possible to run binary search against a tree structure. The general recursive algorithm is going to look like this. Our base case is the same as with any other search. If we happen to find the value that we're looking for at the current node, then we can just return right away. Otherwise, given binary search tree rules, we can compare the value that we're looking for with the value at the current node. If the target value is less than the current value, then we should recursively search left, because we know that all values to the left of the current value, the left branch of the current node, are going to be less than the value at the current node. And therefore, if the target is in the tree, it must be on the left side. Otherwise, if the target value we're looking for is greater than the current node we're currently at, then we need to go look down the right side of the tree. Let's go back to the whiteboard and see that in action. Here's a summarized version of the algorithm on the right side, my Boolean bin search algorithm. If the base case is met where the value I'm looking for is equal, or there is nothing to look here, then I either return false or true. Otherwise, based on the value I see in the current root of the subtree I'm examining, I want to go either left or right. Let's try out these examples, starting out with bin search of 6. We start at the very top node, and we need to go find 6, which is, of course, less than 10. So, not a base case, it's not 10, but we do need to know, or well, we do know that we should go look to the left side of 10 because it's, of course, less than 10. Then we run at the value 4, which is, of course, not equal to 6, but we also know that 6 is greater than 4, so we should go look down the right side of the tree. We run at the value 8. 8 is not equal to 6, but we should go down the left side because 6 is less than 8. And then we finally find the value that we're looking for. Pretty neat. Let's try with a different example. Let's try looking for the value 18. Once again, I start at the very top of my tree. Whoops. Start at the very top of my tree. 18 is greater than 10, so I need to go down the right side. $18 is less than 20, so I need to go down the left side of 20. 18 is greater than 15, so I need to go to the right side of 15. And then I hit my base case where I find the node that I'm looking for. Okay, let's do one more example where I'm looking for a value that is not presently in this tree, which is bin search of 99. I start at the root node, I look at 10, 99 is greater than 10, so I need to go to the right of 10. I find node 20. 99 is, again, greater than 20, so I need to go look at 20's right side children. 99 is greater than 24, so I need to go look at 24's right side children. But there aren't any here, so I hit this base case where I can return false right away. The clever thing about binary search is, once again, just like with binary search on that list that we did in the past, is that we're cutting the search space in half with every single step. Let's retrace this bin search of 18 call one more time. When I make the decision to go left from the root node go right on the root node because 18 is greater than 10, I carve out the entire left side of the tree because I know the value is not there and I'm not going to have to search there anymore. Similarly, when I make a decision to go look down the left children of node 20 here, because 18 is less than 20, I carve away the entire right side of the remaining tree in my search space because I know that the value I'm looking for is not going to be in there. Then when I reach node 15 and I see that 18 is greater than 15, I carve away the values that were on the left side of 15 until I finally reach the node that I'm looking for. So this clever strategy of cutting my search space in half with every single step is going to get me log event performance on a balanced tree. Remember that log event performance is very good. Log event is pretty much, for all practical applications, O of 1 because of how efficiently it tackles large-scale problems. However, there is still the circumstance we have to think about, which is the unbalanced tree. This is the tree where there's several nodes that are lined up on one side of the tree. Perhaps we just had bad luck when we were assembling this structure and we accidentally moved all the values in a particular order down one side. And then the outcome is that we may have to end up searching very deep within the tree to find the value we're looking for. So with binary search trees, performance is going to degrade to O of n, and we lose the benefit of binary search if our tree is unbalanced. If we have a balanced tree though, then we get very, very good performance of searching for values because we only have to look at half the space remaining in our search space with every step that we take. One other point I want to make here, before we return to the README, is that binary search need not actually be recursive. If we look at these return calls here, these return calls are going to return exactly the value of the recursive function call. What that means is it's not actually necessary to combine a composite solution together because the solution is going to be dictated by exactly whatever the recursion tells us. So we could actually implement binary search without recursion by simply having a root pointer and updating that to something like root equals root.right, and then repeating the search process within a loop. Okay, what I've got written here is that observe every step in the search halves the remaining search space, and the search performs as if we knew the exact path to the target node beforehand. This is another really clever thing and way to think about it. Binary search is as if you had guideposts for every single step telling you which way to go. This is kind of like in real life if you had somebody at every street corner giving you directions to go left or right. Based on the searching context, the value we're looking for, and the value of the node that we're currently accessing, we know whether or not to continue searching down the left or the right side of the tree. We talked about performance. Binary search is log event performance on average for a balanced tree because we only have to go up to the maximum depth of the tree, which is of course log of n in a balanced tree. But if our tree is heavily weighted towards one particular side, we may have to end up searching every single node to get to the very bottom, which gives us O of n worst case performance. If we implement it iteratively, like I suggested, we can get only O of 1 stack space. You can also do it recursively, but there's not a huge advantage to doing so. Now compare that to list search, which is always going to be O of n, because then we have to walk the entire list. you could theoretically sort a list and perform binary search on that, but list sorting is actually, well, inserting values into a list in a sorted order tends to be less performant because we tend to have to shift around values and find the index we're looking for. Meanwhile, when it comes to binary search and assembling binary search trees, there are algorithms that can actually give us self-balancing binary search trees that give us, on average, pretty good performance for insertion, while also keeping the tree balanced. We can't quite get the same sort of guarantees with inserting sorted values into a sorted list, because with the array list, we have to either shift all the elements around, and with a linked list, we have to traverse potentially the entire list to reach the node that we're looking for. We've talked about how logarithm performance significantly outperforms linear time performance for large n, to the point where I sometimes compare log of n performance to O of 1 performance. The example I like to tout is that if we have an n equal to 2 to the 30, which is a binary tree that is of depth 30, that is roughly 1 billion values, 1 billion nodes in the tree. Because logarithms are the inverse of exponents, it's only going to take us 30 steps to actually reach the very bottom of the tree. That's pretty cool, being able to look through this entire tree to find a value in just 30 steps. I also leave you this link to bigocheatsheet.com, which was one of your previous readings, which has some pretty neat graphs that show you just how well logarithms scale compared to linear time. All modern database software uses some kind of binary search tree for efficient lookup and storage. There are special BST designs, such as the red-black tree, the AVL tree, etc., that are self-balancing and also quite complicated, so those are out of scope for this class. But wait, trees don't store information sequentially. You told us that last class. How can we maintain some natural semblance of ordering? We can think about this in the perspective of having a database. If you are running Facebook or some other big web application, you have a big database of people, and sometimes you need to linearly iterate over them. However, binary search trees, and trees in general, don't seem to offer that same sequential ordering that we saw with lists. So how can we have a meaningful way to canonically order the elements in our tree that we can view them in a sort of list-like format? Aha! Since binary search trees are ordinary binary trees, we can leverage one of those depth-first search traversal strategies to maintain a given order. Let's go ahead and try an in-order traversal with a binary search tree. Okay, in an in-order traversal, the in part of in order tells us that the parent node should be examined after the left node, but before the right node. So the left node comes first, then the parent node, and then the right node. Let's try performing a in-order traversal on this binary search tree. We start with a root, but we don't examine it because we need to examine the left side first. We go down to 4. We don't examine it because we need to look at the left side. 4 has no left side, so then we're done with the left side of 4. Then we see 4, which means we can now examine it. Then we resolve 4's right side, which takes us to 8. We need to examine 8's left side before we examine itself, which takes us to 6. 6 has no children, so we can just return 6, which is going to resolve 8's left side, so we can return 8. 8 has no right side, which resolves all of 4's right side. And then that resolves all of 10's left side. That gives us the chance to now examine 10 and then resolve 10's right side. We go down 10's right side, we reach node 20. But before we resolve 20, we need to go look down the left side of 20. Before we resolve 15, we need to go look down the left side of 12, which has no children, so we can get 12, which resolves 15's left side. That gives us a chance to resolve 15. Then we need to go down 15's right side. 18 has no children, so we can resolve it right away. And now that we're done resolving the subtree of node 15, we can now resolve node 20. Now we need to resolve 20's right side, starting with node 24. And before we can resolve 24, we need to resolve its left side children, which includes just 21. Now that we've resolved all 24's left side, we need to resolve 24. And then 24 has no right side child, so then we are done with the right side of 20. and therefore the right side of 10, and therefore processing an in-order traversal of this entire tree. Notice how, when we do that in-order traversal, the values we get on the way out for this binary search tree are in sorted order. So this is really, really clever. By walking this tree in a particular way and looking at all the nodes, we can retrieve a list representation of the tree as if we had flattened the tree, and that list representation itself becomes sorted. Another way to look at this is if we just examine visually the tree nodes left to right, and if we draw them in a way that the binary search properties are maintained, and that the child node values are always going to sit between their parent nodes, we'll see that the ordering shows up visually in this tree as well. So if I start with 4, next node is 6, 8, and then 10, and then 12, 15, 18, 20, 21, 24. So this in-order traversal is one way for us to get this sorted order in a linear fashion out of this binary search tree structure. So the result, lookup performed, is in sorted order. We can convert a binary search tree to a sorted list this way in O of n time. You will get to implement binary search on your next project. I do want to make a remark. Not every binary tree is a binary search tree. Don't make the mistake of telling an interviewer that binary tree search is always log of n performance. It's not always the case if you have a binary tree. You should always go ahead and ask, is this a binary search tree? In which case you can start to make those kinds of assumptions. Otherwise, you should play it safe. And remember that you can still search through a binary tree just using that sort of depth first search brute force way that's not quite as performant, but it's going to work for all binary trees. Now I'd like to turn to a different topic, which relates more to recursion than trees. And this is something called tail recursion, which is a special variation of recursion that lets us solve problems that would typically be iterative solutions in a slightly different way. Tail recursion is a special form of recursion where the solution to the recursive case is passed as an argument to the recursive call. Let's go see some examples in tailrecursiontest.java. Remember that range sum method that we had written when we initially learned recursion? Let's do it with tail recursion. We're tasked with adding the numbers from 0 up to the limit that I'm passing in as an argument. And with my tail recursive solution, I'm going to have a rather unique method signature. I'm going to have that limit parameter that I had, but I'll also have a second argument, which is this int solution argument. And what tail recursion is going to do is that it's going to start passing along the solution to the collective problem in the recursive call to the argument. Let's break this down. I've written a wrapper method called range sum, so I have the same method signature, but I'll just use this as a helper to call range sum tail recursive and pass in a solution value of 0 to start. I still have a base case. If my limit value is equal to 0, then I can just return my solution right away, which is the solution to the overall problem. Otherwise, I'm going to return range sum tail recursive of limit minus 1, so I narrow down the problem space, and then my solution becomes the current solution I have plus the value I'm currently examining. So this is really interesting. Rather than returning a composite solution from this call by doing something like limit plus range sum, I'm instead returning exactly the call to range sum tail recursive, where the problem shrinks and the solution is passed forwards to the recursive call, rather than being bubbled up from this return statement here. What we'll observe is that solution is going to start out as 0, which is the, base solution when limit is nothing, and then solution is going to start growing over time, carrying those values forwards to the recursive calls inside the second argument here. For perspective, here was that range sum recursive method. I had a simple base case that just returned 0, and then in my return statement I added the current value I had with the result of the recursive call in a smaller problem space. So what I've essentially done is I've deferred this addition step to the argument of the recursive call, and I've made it responsible for the base case to return that argument rather than just a 0 value here. Okay, let's see some examples. Here my range sum test is going to go through the same test cases that I had with the range sum recursive implementation. Remember that range sum is a wrapper function around range sum tail recursive that simply simplifies the method signature for range sum tail recursive and gives a default value to this solution field. Let's try debugging this as an exercise. I'll go ahead and set a breakpoint for this one, range sum of 3. Let's go ahead and step in to this range sum function and see that I start out with a limit value of 3, which is of course just going to be passed on to range sum tail recursive, so let's step in there. Range sum tail recursive has two arguments, int limit and int solution, where solution is currently set to 0. I don't hit my base case, so I defer the return value result to be what I had called with limit -1 and solution plus limit. It looks like I accidentally jumped out of the function because I hit step over rather than step in. So let's actually restart debugging. I'll go ahead and resume so it ends and start debugging over again. Okay, back here, let's step in to range sum, step in to range sum tail recursive, step over the base case, and then step into this recursive call to range sum tail recursive, where I'm going to sum up the current solution with the current value I'm looking at. Then I go one level deeper. We'll see that my call stack has increased by 1 frame because I need to preserve the calling context. My limit is now 2, and my solution is now 3 because I'd passed that on from the parent calling frame. I skip the base case again. I step in. Now my solution is now the sum of the values 3 and 2, which were passed in these previous frames. Now that I have a limit value of 1, I'm going to add that to the solution that I currently have of 5. Skip past the base case, because that's not going to hit. Step into range sum tail recursive. And now my collective solution has added up to 6, which was passed on to me from these previous calls to tail recursion, this range sum tail recursive. Here I finally hit my base case where the limit is 0, and because I've carried my solution forward in this second argument to range sum tail recursive, I can return the solution argument rather than some base case raw value here. So here when I step over, it's actually going to step me out and start passing out that final total sum of 6 to these return statements. And as I step out, we're going to reach that final call to range sum and get a value of 6. So what we find is that tail recursion behaves a lot like recursion, except rather than accumulating the composite solution on the way up the call stack while these recursive calls return, we instead accumulate the composite solution on the way down the call stack as we pass the composite solution along to these recursive calls. Let's look at another example. This one's get max of list. This is going to get the maximum integer stored inside of a list. My function argument simply has one root list node value, so this is going to be the head of my linked list, and I'll use this get max of list function as a helper function to my get max of list tail recursive function, which has 2 arguments. The arguments needed for the function, and then the composite solution that I'm going to be carrying forwards inside my second argument. I've got a similar base case as I did with range sum, where if my list is empty, then I'll return whatever the default current maximum is. Otherwise, I need to compare my current maximum, which is the solution I have so far, with the value at the current root. If either there is no current maximum, or the maximum I have, or the root payload value is greater than the current maximum, I'll use the compare to method to validate that. If this one returns, if compare to returns a positive number, then it is indeed greater. Then I should replace my current maximum, which is my composite solution so far, with the new maximum value that I've found, which represents the maximum value of the list that I've seen so far. Then I'll recursively return the tail recursive call to get max of list tail recursive, where I pass in the rest of my list, which is root.next, in the maximum I know so far. I do a little bit of praying that eventually, by reducing the scope of my problem, by passing in root.next here, it's eventually going to hit this root equals null case, where the base case is going to return the cumulative solution to the overall problem, which is represented by current max. As reference, here's that getMax of list function written using plain recursion, where I formed the composite solution by combining the two recursive calls, or combining the recursive call with my current payload value. Once again, the distinction is that with tail recursion, I form a composite solution right away, and I pass that on to the next recursive call. And then I return the exact call to the recursive call, because it's going to return that second argument on the way out in the base case. In my plain recursion example, what I do instead is that I perform the recursive call, but then I form that composite solution by combining the solution I have with the solution from recursion in order to form a solution to the overall problem. Let's go through some examples to make sure it works. Get max of list of an empty list should return nothing. It's null. For a list with exactly one value of 0, then the maximum is still 0. Makes sense. Here's my list with 4 values now, with the values 0, 1, 2, and 3. Get max of list is going to give me the value 3. Here, if I try to append a value to the very front, then that new value 9 becomes the maximum of all those values. And if I adjust a value in the middle, then that middle value is going to be the new max of the list. Let's debug this one more time so we have clarity on how tail recursion works. Okay, I'm getting the maximum value of my list, which has the values 9, 0, 5, 5, 5, 2, and 3. I'll go and step into my get max of list function, which is of course the helper function to get max of list tail recursive. I'll pass in the root node and the current maximum value that we've known so far of null. Let's step in. Don't hit my base case, so I need to compare my current maximum, which starts out as null, with the value I have. The value I have, which of course is, bigger than whatever null is, I suppose. We should replace the current maximum, the maximum that we know so far, with the current root value payload, which sets that to 9, the very first value in our list. And then I will go pass that solution forward as current max to the recursive call. I'll step in one more time. Here I have the second node in my list. I'm comparing current max to whatever values at root.payload. And I find that root.payload is not going to be a replacement for the current maximum. Root.payload, as we see in the variable inspector, is actually still 0. Remember, our list was 9, 0, 5, 5, 5, 2, and 3. Let's go and step in one more time. My current maximum remains 9, but then I discover that the root's value of 555 is greater than my current maximum, and this should replace the maximum that I know so far moving forwards. So when I step forward again, my next call to get max of list tail recursive is going to pass in 555 as my current known maximum. I'll keep going, and I'm not going to find a new maximum once I reach the very end of the list, and then I can start to return that value 555 on the way out. So when I step out of this initial call, I indeed get 555 as the value that is the maximum of my list. Okay, so now that we know how tail recursive functions are written, let's make some observations. Unlike traditional recursion, the base case in our tail recursive problem is either going to return a trivial solution or the solution that's passed by the argument, because that is the collective solution that we've generated over these recursive calls. The recursive return statement is going to return exactly the recursive call, because we're going to expect that the base case returns the solution. As a result of this, tree recursion is not necessarily appropriate for tree search. And the reason for this is because we need to have the context of the different branches and the solutions to those different branches of our tree when we were performing the tree search to maybe go find a maximum value. If we use tail recursion, then we have to have the solution right away to pass it on to another argument inside our recursion calls. Now, that doesn't mean you can't have an argument that you can pass on to your recursive calls in traditional recursion. That is something that you may actually have to do when it comes to solving certain problems. But here, the solution to the overall problem is explicitly one of the arguments to this tail recursive function. And we may not necessarily have that composite solution available to us when we are performing tree search, because we can't look down both sides of the tree in advance of, well, actually looking down both sides of the tree. An interesting consequence of this is that every iterative program algorithm can actually be turned into a tail recursive algorithm and vice versa. With traditional recursion, this is not necessarily the case. We used the stack to make recursion possible. We needed to keep the calling context of every function before we called into deeper recursive calls, because eventually those calling contexts would generate a composite solution based on the combined result of the recursive calls. That was possible via the stack, but tail recursion is going to pass that solution forwards. One interesting effect of tail recursion is that it can actually be optimized to take up O of 1 stack space by the compiler, despite the fact that it is still a version of recursion. This is possible because the compiler can actually recognize when tail recursion is taking place, because the recursive return statement returns exactly the recursive call. What's clever here is that this means there doesn't need to be that calling context that needs to be saved that we saw with traditional recursion. If we're going to return exactly the recursive call, that means we don't have to combine any values together to form a composite solution. The solution is passed on and responsibility is deferred to these recursive calls. So what the compiler will do is it'll actually transform tail recursion into a loop, because it knows it doesn't have to preserve the calling context of each recursive call. Which takes us into your next project, Project 3. Project 3 is all about trees and recursion practice. This is a very algorithms-heavy project, and it is actually one of the few that will compile out of the box, so you don't have to do any extra setup. There's opportunity for bonus credit on this project. If you get all test cases passing, you can get up to 10 bonus points here. Otherwise, you only have to get 14 out of 15. I will make a different Project 3 briefing video that you can watch to get yourself caught up, but you can go ahead and get started now by reading the project specification on the homepage. Okay, that's all I've got for today. Thank you for listening, and I'll talk to you next time.